Hi, and welcome to Educator. Our next topic is going to be that of stereochemistry, and that's where we take a look at organic molecules in 3 dimensions, look at their shapes in space. Now, we've talked about isomers before, and our original definition of isomers, or the first way we're introduced to it, is the idea of having 2 molecules who are related simply by their molecular formula. So they're different compounds, but they have the same formula. The atoms are put together differently, have a different connectivity, and that's what makes them unique compounds. Okay, of course, they're different compounds because they are not interconvertible, and that's what makes them unique. Now, the original isomers we have are known as structural isomers or constitutional isomers. These are the ones with different connectivity. So, for example, these 2 alcohols are unique compounds, but because they have the same number of carbons, hydrogens, oxygens, they are defined as isomers of one another. What we're going to look at next is the concept of having stereoisomers. Now, stereoisomers, again, are described as isomers because they are not interconvertible and they're not identical. But they have the same connectivity. All the atoms are put together in the same way, and they differ by arrangement in space only. So only when we look at their 3-dimensional shape do we see a difference in their structures. Let's take a look at a few examples. For example, if we have an alkene, we can have either the cis configuration or the trans configuration, these different arrangements that we can have about the carbon-carbon double bond makes these 2 alkenes unique compounds. They're not superimposable, they're not identical. Because rotation around this double bond is prohibited, then we can't simply flip them to be one side or the other. We call it trans if they're on opposite sides, and cis if they're on the same sides. And these are examples of stereoisomers. They're the same number of carbons, hydrogens, oxygens, and so on, same formula, and they're even put together in the same order. This is a 1, 2, 3, 4 carbon chain, let's say, with maybe a chlorine at carbon 2 and 3. And this is also a 1, 2, 3, 4 carbon chain with a carbon at 2, chlorines at 2 and 3. So only by looking at their 3-dimensional shape do we find a difference. These are called stereoisomers. Sometimes this is just called cis-trans isomerism. Another example where we can have cis-trans isomerism is in the case of cycloalkanes. When we have a ring, let's say we have 2 groups on a ring. Here we have 2 methyl groups in the 1 and 3 position. Here we also have 2 methyl groups in the 1 and 3 position, so both of these molecules will be named as 1,3-dimethyl cyclohexane. But again, when we look at their 3-dimensional shape, we see they are unique compounds because in this case, they are both methyl groups are pointing down, pointing away, and here we have one pointing down and one pointing up. We use the same terminology here to describe cis and trans. We describe 2 groups on a ring as being cis to one another if they're on the same side of the ring. So if we kind of flatten out the ring, you see that you can either be in the up position or the down position, either above the ring or below the ring. So because these 2 substituents are on the same side of the ring, we would describe them as being cis to one another. If they're on opposite sides of the ring, one up and one down, we would describe them as being trans to one another. And once again, these 2 molecules are unique compounds. They're not interconvertible. In this case, it's because of the ring that free rotation around these sigma bonds are prohibited, and we can't interconvert between the 2. So cis and trans molecules are examples of stereoisomers. Another interesting example of stereoisomers that we're going to be spending most of our time with in this section deals with a tetrahedral carbon. So an sp3 hybridized carbon that has 4 different groups attached, so 4 unique groups attached. Okay, now if I were to build such a carbon, and then I were to build another carbon with the exact same 4 groups, and I attach them in the exact same order in 3 dimensions, I would see that I've built 2 molecules that are identical. They are completely identical. So we could draw that on the page as saying, okay, if I draw my tetrahedral carbon, if I have a red up here and a green down here and a blue as a wedge and a yellow as a dash, these 2 molecules as drawn would be described as being super imposable. Every atom on the first structure corresponds exactly with the atom on the second structure when you try and align these two. That's another word for just saying they are identical. But that's the test we're going to use to describe if two stereoisomers are identical, is if we can superimpose them. Now let me show you a little trick here. If I swap any two groups on here, let's take the red and the yellow and replace, switch their positions. When I do that and I try this same test and try to align them, all of a sudden I find that the two tetrahedral carbons are no longer superimposable. They're no longer identical. If I line up the blue and the green, then the red and the yellow don't match up. If I line up the red and the blue, any two colors that I pick to line up, I'll find that the other two colors don't align. Okay, and so now suddenly we have, by doing this switch, we've come up with a new structure. And it doesn't matter which two groups you switch. You could try this at home. So let's switch the red and the green, but keep the blue and the yellow in the same position. When we make that swap, we find that these two groups are now non-superimposable. They are unique compounds. They are stereoisomers of one another. And this now is going to be a little more challenging to see because without working with models, eventually we're going to be able to have to look at this three-dimensional drawing and this three-dimensional drawing and be able to tell by manipulating in our minds that in fact they are non-superimposable and they are unique compounds. Now one more thing I want to demonstrate with these two tetrahedral carbons is they do in fact have a relationship. You might be able to see. It looks as if I had a mirror placed in between the two molecules. One would be the perfect reflection of the other. So we describe these as having a mirror image relationship. That's another relationship that's going to be very important to us in this chapter that we'll come back to. What makes a tetrahedral carbon with four unique groups on it, such as this, special and have this special relationship of being non-superimposable with this mirror image is the fact that this molecule is a chiral molecule. So we need to discuss the term chirality and understand what that means, and then we'll test out a few examples. Okay, what we've just demonstrated is that stereoisomers are going to be possible for any tetrahedral carbon with four different groups attached. A lot of times we identify that carbon with an asterisk, and that carbon can be described as a chiral carbon or an asymmetric carbon or perhaps a chirality center. What we'll find is that when we have chiral objects, they are described as chiral because they have no mirror planes of symmetry, no internal planes of symmetry. Now there are a few rare exceptions of highly symmetrical molecules that have no plane of symmetry but are still not chiral, but we're not going to come across any of those in our introductory lessons. Okay, so what we're going to look for is a plane of symmetry to describe whether or not something is chiral. If an object does have a plane of symmetry, we're going to describe that molecule as being achiral, meaning not chiral. Okay, so let's take a look at some sample molecules and see if we can determine whether or not they might be chiral or achiral. So how about just a plain cyclohexane ring? Now in cyclohexane, we know that it has various conformations. It can be a chair or a boat or a few different chairs. But when it comes to looking for elements of symmetry, what we're going to do is we're going to totally flatten out these rings. We're going to try and make them as symmetrical as possible before we look for symmetry. Okay, now would you describe cyclohexane then as a symmetrical molecule? Does it have an internal plane of symmetry where one half of the molecule reflects on the other half? Well, yes. In fact, this is a highly symmetrical molecule. We can have a plane of symmetry that cuts straight through this molecule here. These three carbons reflect on these three carbons perfectly. In fact, you can even have a plane of symmetry that slices through carbons and hydrogens. So one half of this carbon atom reflects on the other half of this carbon. And then, the point is that the left-hand half of the molecule is the exact mirror image of the right-hand half. So one example of an achiral molecule would be just something like a simple cyclohexane ring. Now what if I were to put a substituent somewhere on the ring? Bromine, chlorine, something. Okay, now is this still a symmetrical molecule? Well, clearly we've taken away some of the symmetry, okay, but there is one plane of symmetry that still exists. In fact, I forgot to mention that this, we can even slice through, for just cyclohexane, we can slice through all 6 carbons, and that would be a plane of symmetry. It reflects these 6 top hydrogens on these 6 bottom hydrogens. Okay, so putting a substituent on the ring takes away that plane of symmetry, but we still have one internal plane of symmetry right here. We can slice exactly through that atom and through these 2 carbons and those hydrogens and reflect this half onto this half. So this would still be, because it has a plane of symmetry, we describe this as an achiral molecule. So maybe we could draw this as a ring with just you know, either a wedge coming out or even a dash coming out. Doesn't matter how we draw that group. How about looking at a carbon-carbon double bond? Such as this. Let's look at an alkene, a carbon-carbon double bond. Let's put one group on here, maybe again a chlorine or a bromine or maybe a methyl, something like that. Now, this is not a plane of symmetry, and this would not be a plane of symmetry. This is not a plane of symmetry because it reflects a white atom onto a hydrogen, okay? But because this molecule is planar, we can use the plane of the molecule as a plane of symmetry, slicing through every one of these atoms and reflecting the top half onto the bottom half. So this, in fact, is also a symmetrical molecule. We describe this as an achiral molecule. So something like this. Let's maybe put a CH3 here, for example. Okay, and this is planar, so the plane of the molecule is going to act as the plane of symmetry. And a lot of times what we can do is we can draw, you could use a dashed line to indicate where the internal plane of symmetry is on the molecule. So there it is for the substituted cyclohexane, and this one has a few planes of symmetry. We can go across this way or this way, and we can also have the plane of the molecule if we were to flatten it out. Okay, how about having a 6-membered ring with 2 groups on it? Does this still have a plane of symmetry? Well, in this case, it does. It has a plane of symmetry right here. And this is a plane of symmetry because we have an atom pointing towards you on the left and an atom pointing towards you on the right. This would be as reflected on a mirror. So anything that is a wedge on one side would have to be a wedge on the other side, just like you would expect for a mirror image relationship. So this too would be an example of an achiral molecule. Now how about if I swapped one of these groups? Instead of looking at the cis disubstituted, how about the trans disubstituted? Now does this molecule still have a plane of symmetry? Well, it is a symmetrical molecule, and a lot of times what you might recognize is it's got a rotational symmetry, okay, but that's not what we're looking for chirality. For chirality, we're looking for a plane of symmetry, an internal plane, and when we try and cut the molecule in half this way, we see that here we have a red atom reflecting up on the top, and here that's reflecting on a hydrogen. So this, in fact, does not have a plane of symmetry, so we would describe this molecule as a chiral molecule, So if we made one a wedge and one a dash, this now would be a chiral molecule. Another example of a chiral molecule was this tetrahedral carbon that we saw. Right? Because it has 4 unique groups, there's no plane of symmetry here because each group has no match to reflect onto. Okay, so we could write that down as an example of something that could be chiral, is a carbon with 4 different groups on it. Remember, we described that as being a chiral carbon or an asymmetric carbon, and that's because it is an example of something that's chiral. Another interesting example of something that's chiral is your hand. You'll see this used in every nearly every textbook that you refer to for organic chemistry. And even though it's planar, the top half of your hand is different from the bottom half. Your palm looks different, has different texture than the top half of your hand. So this is all something that is also something that is described as chiral, and we'll see some examples with that. And we can look for this symmetry in all sorts of different things besides molecules. Like I said, you could use your hand. You could also imagine maybe a chair. What if you had an ordinary chair with arms on both sides and the seat and the back? That's something that is symmetrical. The left half looks exactly the same as the right half. So we could say that a chair is an example of something that is achiral. And then how about if we compared that with a student desk that you might find in a classroom? The student desk that has a chair, but attached to it is a table, and it's usually attached on one side or the other side, right? We have some right-handed desks, we have some left-handed desks, and so that takes away the plane of symmetry. So a student desk, let's call it, is something that is also described as chiral. So one thing we want to know when we're studying stereochemistry is not only the definition of what it means to be chiral or achiral, but then also to identify a given species as being chiral or achiral. It's simply a matter of identifying internal mirror planes of symmetry. Now let me show you something interesting about a molecule that is chiral or achiral. Let me show you, let's come back to our achiral molecule where we had the two groups pointing up right here. And let me draw its mirror image. So I'm going to imagine a mirror here, and then I'm going to try and draw the same structure and draw what I would see if I had a mirror here. So this pointing toward the mirror, just like this one, would be a wedge, and this one on the third carbon down, we have another wedge. This would be the mirror image of this first structure. Now let me ask, what is the relationship of those two compounds? If you had to describe the relationship of these two compounds, how would you describe them? Well, let me build two of them and we can compare it. Hopefully you see the mirror image relationship here, right? They're mirror images of one another. And are these two compounds superimposable? Are they identical? Well, sure. Hopefully you can see that if I just picked this up and moved it over, I would in fact be able to match up every single atom on the first structure with the one on the second. So we describe this as being superimposable. Superimposable or identical. In other words, they are identical to one another. Now let's do the same thing with this second structure. So right here I have a molecule drawn where there's the one on the left is a wedge pointing up. The one on the right is a dash pointing down. Okay, and then let's draw its mirror image. What does that mirror image look like? So we draw another cyclohexane ring. This one is the closest here, and pointing in this direction we have a dash. And then over here we have a wedge. Now let's look at these two molecules again and ask, what is their relationship? What is the relationship? Are these superimposable? And this is where it gets to be a little challenging, and this is where working with models and getting plenty of practice is going to pay off, because we're going to need to be able to see these relationships. Okay, here I have the model of these two. Can I get them to superimpose? Well, if I do that same trick as before, if I lift it up and just try and lay them on top of each other, I see they do not superimpose, because here we have the red atom up and here we have the red atom down. Okay, well, how about if I were to flip it? Can you imagine doing that? Let's try flipping it. When I flip it, same thing happens. I cannot get these to line up. So no matter what manipulations I do, remember, you're free to rotate this around, but we're going to flatten it out and make it as symmetrical as possible. These will not superimpose. These are unique compounds. These are non-superimposable. And these are called, we have a name for these, when you have a chiral object and you have a pair of non-superimposable mirror images, we call these enantiomers. There's a lot of vocabulary in the stereochemistry unit, a lot of new terms and vocabulary that we will need to become familiar with. And so a pair of non-superimposable mirror images are called enantiomers. So let's look a little more closely at this and see if we can come up with some generalizations, okay? I've just redrawn what we drew by hand. We said that these two molecules, when we built them, we confirmed that they are in fact superimposable, while these two molecules, when we built them, we found that they're non-superimposable. And this is in fact a generality that we can determine dealing with chiral and achiral. And I'm realizing right here, excuse me, if there's a little typo. Let's compare chiral to achiral. And if we have chiral objects, all chiral objects have non-superimposable mirror images. So every time you have an object like this that we determine is chiral, it has no planes of symmetry, when we draw its mirror image or build its mirror image, it will always be non-superimposable. Okay, in other words, every chiral molecule has an enantiomer. An enantiomer is something that exists for every chiral molecule. Okay, all achiral objects, on the other hand, are exactly the same as their mirror image. So because this molecule is achiral, it has this internal plane of symmetry, when we build its mirror image, we will always end up with the exact same molecule. Now again, we can extend this to not just molecules like this, but we can extend it to the examples we saw on the previous page. Imagine having a student chair, a regular chair. If you were to build its mirror image and have a second chair sitting right next to it so that they are mirror images of each other, would that be a different kind of chair, or is it the exact same thing? Of course, it would be the exact same kind of chair. Okay, in other words, an achiral molecule does not have an enantiomer. It does not have a unique mirror image. It's the same as its mirror image. But if you had a student desk, if you had a right-handed student desk and you made its mirror image, that would be a new type of desk. It would be a left-handed student desk. So that would be like the enantiomer of that original student desk. And this is where the example of the hand comes into play, and that's why you always see in a textbook, is because you have built in with you at all times is a beautiful pair of enantiomers. Disregarding any slight imperfections in your hands, imagining these are perfect mirror images of one another, they would in fact be non-superimposable. Your right hand is unique from your left hand, and that's because this is a chiral object. It has no symmetry, so when you build its mirror image, which is what you have with your right and left hand, when you build its mirror image, you'll end up with a unique compound. So anytime you are having trouble remembering what enantiomers are, remember that you have a little cheat sheet attached to your arms all the time. So next, let's talk about some nomenclature. How do we tell the world if these two molecules are different molecules? So here we had our original pair of enantiomers that we built. We now know what to call these two molecules, mirror images, non-superimposable mirror images. How do we tell the world that we are referring to this structure and not this structure? We need some systematic rules, nomenclature rules, to describe this three-dimensional shape compared to this one. Okay, and what we're going to do is we're going to, for every chiral carbon that we find, so every tetrahedral carbon with 4 unique groups on it, we're going to name that as either an R or an S configuration. So let's talk about the rules on how to determine whether it's R and S, and then we can look at several examples. Okay, these are known as the Kahn-Ingold-Prelog rules. And our first step is that we need to assign priorities to the 4 groups. We need to prioritize them 1, 2, 3, and 4. We're going to do this based on their atomic number. So we can just look at the 4 atoms attached and rank them 1, 2, 3, 4. Number 1 is the highest atomic number. Number 4 is the lowest atomic number. So if you ever have a hydrogen attached to that chiral carbon, that of course would always be number 4 because that's the lowest atomic number possible. Okay, now what if you have a tie? If you have 2 atoms that are identical attached to that tetrahedral carbon, what you're going to do is you're going to move away 1 atom at a time until you find a difference. So you're going to try and break the tie. We'll look at some examples of that. Okay, if you encounter a double bond in your structure, you can treat that as if you had 2 separate single bonds. We'll see some examples of that as well. So our first goal is to rank the groups 1, 2, 3, 4. We are now going to view this chiral carbon with a very specific point of view. We're going to take the number 4 group. Let's say this yellow is our lowest priority. We're going to hold the molecule in such a way, or view the molecule in such a way that the lowest priority group is pointing away from us. So it's a dashed bond, okay? And when it's pointing away from us, we're going to move from group number 1 to 2 to 3. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, and then we're going to look. If that rotation in moving from 1, 2, 3 is a clockwise rotation, then we describe that chiral center as being an R configuration. Clockwise meaning right-handed. It's like if you turned a steering wheel clockwise, your car would make a right-hand turn. Okay, so clockwise means right-handed. That comes from the Latin rectus. And if the rotation instead is counterclockwise, that's kind of like making a left-hand turn. That configuration is known as S, and that comes from the Latin sinister for left-handed. Okay, so that's how we're going to determine R and S. Let's take a look at our first example. So do we have any chiral carbons or asymmetric carbons on this first molecule? Well, sure. Right here, this carbon has 4 different groups on there, so we would describe that as a chirality center, and that means that we could name this as either having the R configuration or the S configuration. So our first goal is to rank our groups. We have a carbon, oxygen, hydrogen, bromine. Our highest priority group is the bromine, number 1. Next is oxygen. We could just refer to the periodic table if we need to see who has the higher atomic number. Hydrogen is always going to be 4, and so that means this carbon is number 3. So we rank our groups 1, 2, 3, 4. Okay, now what we do is we view the molecule with the lowest priority group, number 4, pointing away from us. Now, if we look at this right here, we see that the hydrogen, number 4, already is pointing away from us because it's a dashed bond. So we already are viewing it from the right perspective. So what we do now is rule number 3. I'm sorry, we go from 1 to 2 to 3. 1 to 2 to 3. 1, 2, 3, 1, 2, 3, 1, 2, 3. Keep doing that rotation. And how would you describe that rotation? Looks like a counterclockwise rotation. And because it is counterclockwise, we call this the S configuration. So this is the S molecule. Let's try another one. Here we have another chiral carbon right here, another asymmetric carbon, and we need to identify the 4 groups and number them. So I only see 3 groups there. Where's the 4th group? There must be a 4th group. Remember, for line drawings, it's common to omit the hydrogen. So the hydrogen, because we have these 2 bonds in the plane and the chlorine is a wedge, there must be a hydrogen right here as a dash. So this is where we're really going to have a firm understanding of line drawings and 3-dimensional shapes. So now I see my 4 groups. We have a hydrogen, chlorine, carbon, carbon. So that allows me to rank chlorine as number 1 and hydrogen as number 4. But now we have a tie. Okay, and now we look back at our rules. We say in the case of a tie, we're going to move away just one atom at a time until we find a difference. So let's ask this. What 3 groups are attached to this carbon? I know it's attached to the chiral carbon. What are the other 3 bonds? Well, it's just a CH3, isn't it? So we have a hydrogen and a hydrogen and a hydrogen attached. Let's come over to this carbon and ask the same question. What are the 3 bonds to this carbon? Well, this has a carbon and then a hydrogen and a hydrogen. So now we've broken the tie, and once again we're going to look to the atomic number, which has the highest atomic number. This carbon beats out the hydrogen, so this is going to be group number 2, and this is going to be group number 3. So ranking the groups 1, 2, 3, 4 sometimes requires a little work here. Okay, next we're going to make sure our lowest priority group is pointing away. It's doing that. It's a dashed bond. So what do? We move from 1 to 2 to 3, and we keep doing that. 1, 2, 3, 1, 2, 3, 1, 2, 3. And what does it look like here? Now it looks like we're doing a clockwise rotation, so this is going to be the R configuration. Let's see a few more examples. How about this structure? Do we have any chiral centers? In this one, we're looking for a carbon with 4 different groups on it. Well, yeah, it looks like here where we've shown some stereochemistry, this looks like a chiral carbon, and we have our dashed hydrogen is missing from the structure, so we can add that in to make sure we see all 4 groups. Okay, and what are the atoms of attachment? We have a carbon, carbon, hydrogen, nitrogen. So the first assignment we can make is that nitrogen is number 1 and hydrogen is number 4. And then we have these 2 carbons being in a tie. So let's look at them one by one and see what's attached. So what do we have on this carbon? We have an oxygen and then a carbon and a carbon. And what do we have attached to this carbon? Well, now we have a double bond, and if we refer back to our Coning-Gold-Prelog rules, it says that you can treat a double bond the same as if it were 2 single bonds to that atom. So what we have for our 3 bonds is we have an oxygen and another oxygen and a hydrogen. Okay, now what I want you to be careful of is avoiding the temptation to kind of add these groups up and see which total is higher. We're not doing that. We're simply looking for the highest priority group. So they each have an oxygen, so it's like that's a tie. So then we move to the next highest priority. This has a carbon, and this has an oxygen. Okay, so the second oxygen wins here. So this is group number 2, this carbonyl group. This whole group attached to the chiral carbon is group number 2, and this whole group is going to be group number 3. So now we've ranked our groups 1, 2, 3, 4. And then what do? We move from 1 to 2 to 3. And we keep doing that. Make sure you keep making a complete circle and keep doing the rotation. 1, 2, 3, 1, 2, 3, 1, 2, 3. And this looks like a counterclockwise rotation. So this is the S configuration. The S configuration. Okay, how about the next one? This looks like our chiral center. That's the only chiral carbon there is. And we have a hydrogen here, still a dash. We'll look at some examples where it's not a dash next. So he's group number 4, and now we have a 3-way tie. All 3 of these are carbons. So let's see which one is going to win. Now again, it might be tempting to say, wow, look at this big group. This must be the number 1 priority. But again, we're not doing that. We're going to have a systematic approach. And that means we're just simply going to move out 1 atom at a time and decide which one is the higher priority. So what does this carbon have attached to it? There's going to be 3 bonds from that carbon. There are 3 hydrogens, hydrogen, hydrogen, hydrogen. This carbon has a carbon and then 2 hydrogens. This carbon has a carbon and a carbon and a hydrogen. So right away, just moving out 1 atom at a time, we've already broken the tie. Who's our number 1 priority? This group up here. And then this group is number 2. And then this methyl group over here is number 3. So now we go from 1 to 2 to 3. 1, 2, 3, 1, 2, 3, 1, 2, 3. We see that it's clockwise. This is the R configuration. Very good. How about the next one? Now we have a case where when we add in our missing hydrogen, we see that this is now a wedge instead of a dash. So we need to figure out what to do in that case. Let's rank our groups first. Who wins? We have a carbon, iodine, hydrogen, and chlorine. Well, iodine has the highest atomic number, so that's number 1, chlorine, and then carbon, and then hydrogen. So this turns out this oxygen over here, we never were concerned with that because we didn't have a tie. So we just look at the 4 attached atoms. Okay, and now we want to move from 1 to 2 to 3, but this hydrogen, this lowest priority group, is in the wrong direction. Well, let me show you something. If we're holding this molecule so that the lowest priority group from you is pointing away, let's say we're going in this direction to do 1, 2, 3. The rotation that you see is counterclockwise. Guess what rotation I see from my point of view? I see clockwise. So if you see the exact opposite. So if your lowest priority group is exactly in the wrong position, the opposite position, all you need to do is reverse the rotation that you were going to do. So let me show you what we're going to do. We're going to go from 1 to 2 to 3, and then we're going to back it up and go backwards, and instead we're going to go from 3 to 2 to 1. Okay, so number 4 is a wedge. So we're going to reverse our rotation. In other words, we're going to go from 3 to 2 to 1, and then look at that rotation. From 3 to 2 to 1, this is a clockwise rotation, and clockwise is always the R configuration. So if your lowest priority group is a wedge instead of a dash, it's really just as simple to do it. We just have to remember that the correct orientation, the correct point of view, is one which has the lowest priority group pointing away. So that's when we're going to reverse it. Okay, and how about this last group? How about this last group? If we try and assign the configuration R or S, okay, bromine is number 1, hydrogen is number 4, as always, if you have a hydrogen. And how about the other two groups? When we go to rank these 1, 2, 3, 4, what do you see? Well, this is a tie. This is a carbon and a carbon, and they're both CH2s. And then when we move out, these are both CH3s. So these two groups are identical. So we're not going to be able to number this 1, 2, 3, 4. So what does that do to this chiral center? Does that make this R or S? Well, it's kind of a trick question, isn't it? Because these two groups are identical, that means this carbon atom in this molecule has a plane of symmetry. This is an achiral carbon. So it is not R or S. So R and S configuration is only something that we consider for chiral carbons, meaning a carbon with 4 unique groups attached to it. And if you ever find that you can't rank them 1, 2, 3, 4, and you have a tie, that means you're maybe looking at the wrong carbon in order to assign your R and S configuration. Let's get some practice drawing stereoisomers. Let's say we were asked to draw S2-bromopentane. How could we do that? Well, we could draw pentane, 1, 2, 3, 4, 5. So there's pentane. And on carbon 2, we have a bromine. And what we're going to need to decide, what are our two choices? Well, that bromine can either be a wedged bond or it can be a dashed bond. And only one of them is going to have the S configuration. Now, you could spend an awful lot of time thinking this through in your head and planning it out and trying to get the right answer right off the bat, but that might turn out to be a pretty big waste of time. My advice is to just guess and pick one of them. Let's say we want to have it as a wedge. And then what can we do? We can check to see if we made the right guess. Okay, bromine would be number 1. And between these two carbons, we have a methyl and we have this propyl. This has an extra carbon attached, so this is number 2. This is number 3. And our hydrogen is pointing back. So did we make the right guess? Did we make the right guess? No, this looks like we drew the R configuration. So guess what we have to do? All we have to do is just erase it. I'll just cross it out so I can leave my work here. But I just made the wrong guess, and it's just the bromine as a dash instead. And you could confirm this if you want, but this, in fact, would be the S configuration. Okay, so that a lot of times we can, it's a lot faster to pick one of the stereoisomers and then confirm it rather than try and guess in your mind what's going to be the appropriate one. So that would be S2-bromopentane. Now, what if I asked you to draw the enantiomer of S2-bromopentane? And we already see what the structure of the S enantiomer looks like, and if I wanted to draw the other enantiomer, okay, there's two methods, there's two approaches we can take to this problem. One approach is we could draw the mirror image, because we know the definition of an enantiomer is that they're mirror images of each other. So we can imagine a mirror to the side or to the bottom, and maybe we could draw it like this and draw the bromine here. This would be the mirror image of this if I had a mirror right here. Or if I had a mirror right here, you could see it. And so that should be the enantiomer. That's one possible way to do it. Some students have an easier time drawing mirror images than others. Okay, but there's another method we can have, and that is, what we can do is we can invert all of our chiral centers. And by invert, I mean swap two groups. So in this case, we're going to keep our carbon chain fixed, but instead of having the bromine be a dash, our bromine is going to be a wedge. That's another way to draw an enantiomer accurately, and so whichever method works for you, they both should result in the right answer. Now, are these the same answer? Are these the same compound? You see that? Well, sure. If I take one and I simply flip it over, they should superimpose. If I flip over one, the bromine that was a wedge becomes a dash, and they will line up very nicely. Now let's check the configuration here. We can do it on this one. Here we have bromine is 1, propyl is 2, and the methyl is 3. It looks like this was the first guess we had up top here, isn't it? This is 1, 2, 3. This is the R configuration. And how about this one? If this is the same molecule as this, it should have the same configuration. Let's check that. This is number 1. This is number 2. This is number 3. And I go 1, 2, 3, but where's my lowest priority group? My lowest priority group is actually a wedge, so I'm going to have to reverse this and go backwards and go 3, 2, 1, 3, 2, 1, 3, 2, 1. Yes, this is in fact also the R configuration. So either one of these got to the right answer. And something that we can observe here is that enantiomers have opposite configurations. They have opposite configurations. So if one enantiomer is the S configuration, the other enantiomer must be the R configuration. That will always be true. And even if you have multiple chiral centers, all of the configurations in the chiral centers of one enantiomer will be the opposite in the other. Now I'd like to talk about a shorthand notation we can use to draw chiral centers. And these are known as Fischer projections. And here's the definition of a Fischer projection. What we're going to do is we're going to view a tetrahedral carbon in a very unique, from a very unique perspective. Usually we draw tetrahedrals or tetrahedral carbons or review them in such a way that two bonds are in the plane, so it's easy to draw, and one is a wedge and one is a dash. That's usually how we draw our drawings. For a Fischer projection, what we're going to do is we're going to hold the chiral center this way, or the tetrahedral carbon this way, so that only the carbon atom is in the plane. The two bonds on your right and left are projecting out towards you. It's like you can reach out with your right and left arms and hold on to these atoms on the side, these groups on the side, and the top and bottom groups are pointing away from you. They're actually dashed going back into the plane. Now, if we always view the tetrahedral carbon with this exact perspective, then we don't need to use the dashes and wedges. What we do in a Fischer projection is we project the wedges back into the plane and project the dashes forward into the plane, and we draw it simply as a cross. And so even though this is drawn as all straight lines, none of these bonds are actually in the plane. This is a very special convention, and it means that these side groups are wedges. Kind of looks like a bow tie, doesn't it? Some of my students tell me that that's a way that it helps them remember what a Fischer projection looks like. These side groups are actually wedges, and these top and bottom groups are dashes. Okay? And by convention, the carbon chain is usually drawn in this vertical position. So although you can look at a tetrahedral carbon this way or this way, there's a few different points of view you can have. If this was the carbon chain, usually we put that in the vertical position. We'll see lots of examples of this. So here's one example. Let's say we have this Fischer we're asked to draw this Fischer projection. Okay, we have 4 carbons. We have a chlorine as a wedge here. And what we're going to do for the Fischer projection is instead of viewing this molecule from the side, we're going to be tipping the molecule up like this so that we're viewing this tetrahedral carbon as defined by the Fischer projection. As defined, the carbon chain is top and bottom pointing away from you, and the two side groups, in this case chlorine and hydrogen, are projecting out toward you, are wedges. Okay, and in this perspective, where do you see the chlorine? It's on your left. So when we draw the Fischer projection, let's number our carbons here. Let's say 1, 2, 3, 4. Okay, so carbon 1, let's put this up here. We have a 1 carbon chain up here. And then on the bottom, we have this 2-carbon chain, CH2, CH3. So this is 2, and this is 3, and this is 4. So I'm drawing here the backbone of the Fisher projection. And what we're going to see is when we view it like this, so that the methyl group is up and the ethyl group is down, the chlorine should be on our left. And that would be an accurate Fisher projection. Now, that's great if you have a model and you can pick it up and move it, okay? But if we don't have a model, I think another good strategy you can use is, rather than taking the model and picking it up and moving it, is we can pick ourselves up and move our point of view. So if we were to leave this molecule in the plane as drawn, what would be the perspective that I would need to take to view this molecule so that I see this picture, with the chlorine and the hydrogen projecting out toward me and the methyl up top? Well, what I would need to do, how about if I laid down on the bottom here and viewed the molecule like this? If I were to lay down in that position, the methyl group would be aligned with my head, the ethyl group with my feet, and looking up in this direction, where would you see the chlorine? If I'm in the plane, the chlorine would be a wedged bond, which would be on my left. So we could have this little person saying the chlorine is on my left. And using the stick figure is a nice way to maybe see it from the proper perspective. Another thing you can do, that if you have some time to check your work, is you can check the configuration. If you've drawn the proper Fisher projection, you should still have the same configuration that you had in the lawn drawing. So what was the configuration of this carbon 2 here? Was it R or S? We have number 1 here, number 2 here, number 3 here, number 4 here. Our lowest priority group is pointing away, as it should. So we go from 1 to 2 to 3. 1, 2, 3, 1, 2, 3, 1, 2, 3. This was the R configuration. Let's check to see if it's still the R configuration. Same priorities. Chlorine is 1, ethyl is 2, methyl is 3, hydrogen is 4. We move from 1 to 2 to 3, and now let's check our lowest priority group. Where's our lowest priority group? Is it pointing away like it needs to be? Well, it's in this side position. What's the definition of the side position of the horizontal groups? Remember that bow tie, that side position, it's like it's coming out towards you. You can grab it with your right and left hands. It's a wedge. So what do we do if our lowest priority group is a wedge? We reverse our direction and we go 3, 2, 1, 3, 2, 1, 3, 2, 1. So sure enough, we did draw the correct configuration here. These both have the R configuration. Now, what's very nice about being able to draw Fisher projections is that it allows us to draw chiral centers very, very quickly, because we don't have to worry about dashes and wedges. It also makes it super easy to draw mirror images, because now we don't have to worry about dashes and wedges. Nearly everyone, even the most artistically challenged or spatially challenged student, can draw the mirror image of this Fisher projection. We have a hydrogen closest to the mirror, we have a chlorine further from the mirror, we have a methyl up top, and we have an ethyl down below. Just like that, we drew the mirror image. Much, much easier to draw it for a Fisher projection than a line drawing. So I have a feeling that as you get comfortable with Fisher projections, you will very likely prefer to use them if you have a choice on how to draw your chiral centers. And what should the configuration of this mirror image be? Since this is a chiral molecule and we just drew its enantiomer, I think this better have the S configuration. I've just inverted my chiral center. Look, if you compare these two, we just swapped the position of the hydrogen and the chlorine, and sure enough, we go from 1 to 2 to 3, but then we back it up again, 3, 2, 1, 3, 2, 1, 3, 2, 1. This is, in fact, the S configuration. So we just drew the Fisher projection of this molecule and then drew its enantiomer very quickly. One other very nice use of Fisher projections is if we have to assign the configuration where if our number 4 group is in the plane of the page. Let me redraw this in case it's a little too low to the bottom of the screen. If we were given this molecule and we were asked to assign it as the R or S configuration, we would have a hard time doing it, because our lowest priority group is not it's not a wedge projecting out toward you. It's not a dash pointing away from you. It's in the plane, which means it's parallel to the plane. and we don't have any rules for that. So in that case, I think the easiest, one of the quickest and easiest strategies is to view this molecule as a tetrahedrocarbon with this orientation so that you can convert it to a Fisher projection. So what do you think? If I do this, if I view it from this angle, here's the tetrahedrocarbon, I see it. What groups do I have on the top and the bottom from this perspective? Looks like I have a hydrogen aligned with my head and a methyl group aligned with my feet. And then here's the tricky part. I have two groups on my right and left. They're both coming out toward me. And where is this OH? If I am in the plane of the board, the OH is going to be on my left-hand side. Very good. If you can do that with a little practice, you've got Fisher projections down, piece of cake. And now what's nice about a Fisher projection is by definition every group is either a dash or a wedge. So it's always a simple exercise to assign the configuration. So now all we do is we assign our priorities. Oxygen's number 1, hydrogen's number 4. And for these two carbons, since this one has an oxygen attached, he's a higher priority than the methyl. So we rank our groups 1, 2, 3, 4. We move from 1 to 2 to 3. And then we check our lowest priority group. Where is it? It's in the up position. And what does that mean? That means it's pointing away from us, just like it should be. So we keep our configuration 1, 2, 3, 1, 2, 3, 1, 2, 3. And what do we have here? We have the R configuration. Very simple, rapid way to assign configurations if your molecule is drawn in such a way with the lowest priority group in the plane. Another example where picking your body up and moving it is going to be a good strategy in getting the proper perspective. Now let's take a look at some molecules that have two chiral centers and see what we can do with those. Here we have an example of 2-bromo-3-chloropentane. I've drawn them both here as wedges. Now, because this molecule has two chiral centers, each of them can be described as being the R or S configuration. And so I've put some parentheses out here in anticipation of that. Let's complete the name of this molecule because the stereochemistry, the configuration, is going to be a part of the complete name of a molecule whose three-dimensional shape is given. So here on carbon 2 we have a bromine. Let's determine that configuration. This is group number 1. Let's write them without making too big of a mess. Group number 2, group number 3. So we go from 1 to 2 to 3, and our lowest priority group is a dashed hydrogen. So we go 1, 2, 3, 1, 2, 3, 1, 2, 3. So at carbon 2, we have the R configuration. So we're going to call that 2R out front because we have to say which carbon we're describing. And then on carbon 3, we have a chlorine. And this chlorine has group number 1 and group number 2 and group number 3. And our lowest priority group is pointing away like it should. It looks like this is also the R configuration. So this stereoisomer that's drawn is described as 2R3R, 2-bromo-3-chloropentane. And it's just simply put out in the very front of the name in parentheses is where we put all our stereochemical information. Okay, how about if I wanted to draw the enantiomer of A? We'll call this molecule A for short, the enantiomer of A. Well, remember there were two ways we could do it. We could either draw the mirror image. Now, as our molecules get more complex, you might imagine the mirror images are going to be a little more challenging to draw. So I would recommend, or personally, what I would think would be the easiest way to draw the enantiomer is to keep my carbon chain the same. So bromine is still on 2 and chlorine is still on 3, but I would invert the chiral centers. So where they were both wedges, they are now going to be both dashes. And I automatically know that this is now the enantiomer of A. Let's call this molecule B. And what do you think the configuration is going to be for B? Well, it must be the opposite now of A, so it's going to be 2S, 3S. Of course, you can check all that later. Go back. That's some very good practice that you can get. How about the Fisher projection of A? If I want to do the Fisher projection, now we have, again, our carbon chain. Let's number it so we can get oriented. 1, 2, 3, 4, 5 carbons. So we have a methyl group, and then carbons 2 and 3 are both chiral centers. So our Fisher projection now has 2 horizontal lines. So in fact, Fisher projections are ideal for drawing molecules with multiple chiral centers because it's greatly simplified in this format. Okay, and what we have to decide then to draw an accurate Fisher projection for A is where do we locate the bromine and the chlorine? Are they going to be on the right or left on each carbon? So we have to get the proper perspective, and let's see if we can do that using our line draw, using our stick figures. For carbon 2, what would be the proper point of view to view carbon 2 so that the methyl group is pointing up and away from me, and then the two groups on carbon 2, the hydrogen and the bromine, are both projecting out toward me as wedges? Well, we're going to have to come up from above the molecule looking down, and now that's exactly what we see. We see our bromine and our hydrogen on carbon 2 both coming toward me. Carbon 1 and carbon 3 are both pointing away from me. And where is that bromine? If I'm lined up in this perspective and I'm in the plane, the bromine is going to be on my left. The bromine is going to be on my left. So on carbon 2, I'm going to draw the bromine on the left, hydrogen on the right. Now how about for the chlorine? I can't stay up here with this same perspective and view down at the chlorine because now the chlorine isn't coming toward me, it's pointing away from me, so that's the improper perspective. So the easiest thing for me to do is pick myself up and move myself down here and view in this direction. Now I'm looking at it from underneath the plane of the molecule and looking up, and when I do that again, carbon 1 always needs to be aligned with my head. Where is that chlorine? If I'm in the board, that chlorine is coming down into my right. The chlorine is on my right. So when I come up to carbon 3 here, that's what I see. And there's my Fisher projection of A. Now we can confirm that we've done it correctly. This should still be 2R, 3R. In fact, it is. And let me show you this molecule. See, I think I have it built here. So here we have the bromine and the chlorine as both wedges on my 5-carbon chain. And let's take a look at what that Fisher projection is. The Fisher projection is actually viewing the molecule like this so that the bromine and hydrogen here are coming out toward you. But then this carbon also comes out toward you. So what we've done is we've rotated the molecule to have this confirmation for a Fisher projection. So in a Fisher projection, all the chiral centers have the two groups pointing out toward you. So the molecule kind of wraps itself around like this. So the methyl group is at the very top, ethyl group is the very bottom. We see that the bromine is on our left and the chlorine is on our right. And what we did over here was, instead of having the model, because we didn't have the model to pick up, what we did is we viewed the molecule from the top looking down over here, and that's how we saw the bromine on our left. And then we came down here and we viewed the molecule kind of like this, looking up. And when I do that, now I see that the chlorine is on my right. Okay, so a little practice with models, again, will really pay off here. Ultimately, though, we need to be able to work just on paper and with these three-dimensional drawings. And so a little practice with both gets you up to speed very quickly. How about if I wanted to draw B? Again, once I have the Fisher projection of A, the Fisher projection of B is very straightforward. We just draw its mirror image. So methyl at the top, ethyl at the bottom. And on the top carbon, we have a hydrogen on the inside and a bromine on the outside. On the next carbon, we have a chlorine on the inside and a hydrogen on the outside. There it is. We just drew the mirror image of B. This must be 2s, 3s. We can confirm that if we wanted to. And what is the relationship between A and B? Because A is chiral, because B is its mirror image, A and B are enantiomers. Non-superimposable mirror images. Okay, are there any other stereoisomers that exist for 2-bromo-3-chloropentane? We have one example here in this line drawing where they're both wedges. We have one where they're both dashes. Are there any other arrangements we can have? Well, sure, we could have one as a wedge and one as a dash. So here are the other possibilities we can have. We've already seen A and B where we have wedges and dashes. What if we were to have one wedge and one dash? This now would be another unique stereoisomer. Let's call this molecule C. And just by referencing it to the structures A and B we've already drawn, we even know the configuration. The configuration matches A here, so it's 2R, but then it's the opposite for the next one, so it would be 3S. So we have this molecule, and instead we can make the bromine the dash and chlorine the wedge, and this too would be a unique compound. This molecule we can call D, and this has 2S, 3R. We could draw the Fisher projections of these as well. And these would be good to practice with. In drawing these Fisher projections, you can use the stick figures, you can use models, but just in comparing it to the Fisher projections you already have for A and B, we can see that for C, it's going to have the bromine and the chlorine both on the left. And then for D, it's going to have the bromine and the chlorine both on the right. Okay, so what is the relationship then between these next two stereoisomers that we've drawn? Looks like their configurations have changed. We've gone from RS to SR. Looks like they are mirror images of each other that are non-superimposable. And yep, you might guess that these are also enantiomers. So we have another pair of enantiomers. So these are all the stereoisomers of 2-bromo-3-chloropentane. The question that you might be asking is then what is the relationship between A and C? So A and B are enantiomers of each other. A and C are clearly stereoisomers because they're both 2-bromo-3-chloropentane. They have the same connectivity. They only differ by their stereochemistry. And the way we describe those two structures is we call them diastereomers. They're called diastereomers. And pretty much the definition of a diastereomer is a stereoisomer that is not an enantiomer. So if you have two molecules that you decided are stereoisomers, they're non-superimposable, and they have the same connectivity, you really only have two choices. They are either going to be enantiomers or diastereomers. So do we have any other diastereomer pairs when we look at these four structures? What other compounds can be described as diastereomers of each other? Well, A and C are diastereomers, but A and D are also diastereomers. And the relationship of B to either C or D would also be diastereomers. So A and D, or B and C, or B and D. So any other combination other than the enantiomers we describe as diastereomers. So in other words, all stereoisomers are either enantiomers which we describe as non-superimposable mirror images. They will always have the relationship. Whether you can see that or not, they'll always have that relationship. Or we're going to describe them, all other possibilities are called diastereomers. Have the relationship of being diastereomers. So they are non-mirror images. Another way that we can distinguish between enantiomers and diastereomers, if you compare structures A and B, you see that all of our chiral centers have been inverted. All our wedges have been turned to dashes. And for C and D, every wedge is now a dash, every dash is now a wedge. So another thing that we can look at for enantiomers is that all chiral centers are inverted. Where for diastereomers, if you have multiple chiral centers, if you invert some but not all, then you'd be at diastereomers. Not all chiral centers inverted. Only some have been inverted. So if you, let's say you have 10 chiral centers. If you invert all 10 chiral centers, that structure would be the enantiomer of the original. Any other combination, if you just inverted 1 or 2 or 5 or 8, then all those structures that you could draw would be diastereomers. So we'll find that you can have many, many diastereomers, but only one enantiomer. Only one molecule would be the exact mirror image, and with all the chiral centers being inverted. It turns out the possibility for the number of stereoisomers is you could have 2 to the n stereoisomers possible, where n equals the number of stereocenters. So stereocenters, the term stereocenters can refer to chirality centers, chiral centers, like chiral carbons. So you could have an R and S possibility. But another possibility for stereoisomerism is if you have a double bond, you can have cis and trans isomerism. So maybe double bonds or rings can, groups being cis or trans on a ring, cis or trans on a double bond. All those stereoisomers, we can have 2 to the n possible. So because 2-bromo-3-chloropentane has 2 chiral centers, that's why we had 4 possible stereoisomers that are shown here. Let's take a look at another example. How about if we wanted to draw all stereoisomers of 2,3-dichlorobutane? Now, what would be a systematic way of doing that? We could draw a 4-carbon chain. There's butane, and we have a chlorine. Let's draw them both as wedges to start off with. That would be one possible stereoisomer. Turns out that this is 2R, 3R. I'll let you check that on your own. And we can call this structure A. We could draw it as a line drawing, or we could draw it as a Fisher projection. Again, I'm just going to draw the Fisher projection. And you could confirm that on your own later and try it. One chlorine is going to be on the left. The other is going to be on the right. This would still be A. And what would be another stereoisomer that we could draw? How about the enantiomer of A? We could draw the mirror image of A, either as the Fisher projection This is now a unique compound. We'll call it B. Or as the line drawing. The line drawing would have, instead of both chlorines as wedges, it would have both chlorines as dashes. This would be 2S, 3S, and that would be structure B. That would be the enantiomer. So this is a pretty systematic approach. We could draw both as wedges and then both as dashes. What would be another possibility? Well, we could draw one as a wedge and the other as a dash. So this is clearly a unique compound. We would call this 2R, 3S. And our top carbon here stayed the same with the chlorine on the left, but now the bottom carbon moved the chlorine over to be on the right. So this is structure C. And now we could draw its mirror image. So it's useful to draw stereoisomers as pairs of enantiomers, pairs of mirror images with inverted chiral centers. Hydrogens on the inside, chlorines on the outside. And that would be the same structure, but instead of a wedge and then a dash, we could have a dash and then a wedge. And we would call this structure D. Okay, but there's a problem with this analysis. There's a problem here. I want you to compare these two Fisher projections, or even these two line drawings. Are these in fact unique structures? Can we take this line drawing and just rotate it in the plane and turn it over like this and have it align with this first structure? And the same thing with this Fisher projection. I could take one Fisher projection and just rotate it 180 degrees to line up with the other? You can, in fact, do this. So what we're observing is that this molecule is not a unique compound. These two are superimposable. So these are not structures D, as we might have guessed. We ended up, even though we drew the mirror image, we still drew the same molecule. We had a repeat of a structure we'd already drawn. So what's going on here? Why do we not have 4 possible stereoisomers here? Well, let's take a look at closer at this structure C. Again, I've just redrawn. We have it as the line drawing that are superimposable, or the Fisher projections that are superimposable. And what's happening, the reason our mirror image is superimposable, is identical, is because we have a plane of symmetry in C. And anytime you have a symmetrical molecule, remember the mirror image is identical as to the original structure. So what we have is a very special case here where the carbon has a plane of symmetry which reflects one chiral center onto another. That's a very special kind of symmetrical molecule. It's called a meso compound. So in other words, it does have chiral centers. It does have 2 chiral centers. We can name those as R or S. But the molecule as a whole has a plane of symmetry that reflects one chiral center onto the other chiral center. And for those unique compounds, we call them meso compounds. Okay, because it has a plane of symmetry, C is achiral. It is no longer chiral if it has a plane of symmetry, and if it's achiral, C does not have an enantiomer. Of course, it has a mirror image. Everything has a mirror image, but what makes it not its enantiomer is the fact that the mirror image is superimposable, is identical with the original structure. So in this case, what we see is that there are only 3 stereoisomers possible for 2,3-dichlorobutane. There are not 2 to the N, as we just said that we can have as a maximum. 2 to the N represents a maximum number. And what we said is actually there's 2 to the N that are possible, but in a case of a molecule that is kind of symmetrically substituted, any 3-dimensional arrangement that gives symmetry from one half to the other through an internal plane of symmetry means that we're no longer going to have them occurring in pairs, because that symmetrical molecule is not going to have an enantiomer. If we take a look at this molecule, here we have 2,3-dichlorobutane. We have a chlorine as a wedge and a chlorine as a dash. This looks like an asymmetric molecule, but if we rotate this around so that we try and make it symmetrical. In fact, remember, that's what the Fisher projection does for us, is it makes it a symmetrical molecule. Now we see that, in fact, this can be cut in half. The top half reflects on the bottom half. So what we can do here is we can even see this in the line drawing. If we rotate this about this single carbon-carbon bond, if we were to look at this molecule in this conformation, it would be a little easier to see how, in fact, that it is a symmetrical molecule and it would not have an enantiomer. If I drew these both as wedges or I drew these both as dashes, it'd be the same molecule, I just flipped it over. If I draw them both as wedges, it's the same exact molecule as if I draw them both as dashes. So keep in mind, when you're looking for symmetry, when you're looking to determine whether something is chiral or achiral, make sure you rotate it around and get it in the most symmetrical conformation possible so that you don't miss any potential symmetrical planes of symmetry. Now, one more thing that we should talk about that's important for stereochemistry is the concept of optical activity. This is one of the physical properties that we can discuss for stereoisomers. And what's known is that chiral molecules, so again, molecules that do not have an internal plane of symmetry, chiral molecules rotate a plane of polarized light. For that reason, chiral molecules are called optically active. They are described as being optically active because they rotate a plane of polarized light. This angle of rotation, called alpha, the angle that it rotates is measured by an instrument called a polarimeter. Now let's see what it means to be polarized light and how that plane might be rotated. This is kind of a cartoon of what polarized light looks like. Imagine if you were looking directly at a beam of light. Let's see what ordinary light looks like. Ordinary light, if you're looking straight at it, okay, light occurs, it oscillates, and so if you're looking straight at it, it's going to be coming as a wave toward you, so you're going to see it oscillating, but it's going to be going in every direction. So ordinary light has oscillating waves of radiation going in every direction. And what a polarimeter does is it filters that out so that all you see is a single plane of oscillations of the electromagnetic field. So we can show it like this. Now if you take this polarized light and you pass it through a chiral object, a chiral sample, that plane is going to rotate. And it's going to rotate one way or the other. If it rotates in this direction, we describe that as having a positive angle, so maybe a plus 10 degrees or 20 degrees or 90 degrees. And we describe those molecules as being dextrorotatory. They have a right-handed clockwise rotation. If the molecule rotates in the opposite direction, we describe that angle as being a negative angle, and we describe those molecules as being levorotatory. We use a little L or a little D to describe these molecules, and that is how we describe it when we see a counterclockwise rotation. So chiral molecules are going to be optically active, and we can measure their alpha. And achiral species, something that is not chiral, are not optically active. In other words, if you put them in a polarimeter and you pass a beam of polarized light through it, that beam is going to pass through unchanged. So in other words, alpha equals 0 degrees for an optically inactive species, such as something that is achiral. So what are some other physical properties of stereoisomers that we can take a look at? Turns out that if we're comparing enantiomers and the relationship of enantiomers, we'll see that they have identical physical property. Every physical property that you want to measure, things like its boiling point or melting point or solubility or its NMR or its IR spectra, those sorts of things, they're going to be exactly the same. They will be completely indistinguishable except for this optical activity. It turns out they have equal and opposite optical rotation. So if one enantiomer rotates it clockwise, the other enantiomer is going to rotate it counterclockwise. One will have a plus angle and the other will have a minus angle of the exact same magnitude. When we're comparing diastereomers, stereoisomers that are not enantiomeric, that are not mirror images of each other, they just have different physical properties. So again, anything you can imagine, boiling point, melting point, their optical rotations, their NMR, their solubilities, everything you can imagine. They may coincidentally be similar, but they are not going to be identical. So let's take a look at some examples. Here we have some sugar molecules, and sugar molecules are definitely well suited for these Fisher projection because sugar molecules often have multiple chiral centers, so we can draw them very easily, showing the configuration about each of these polyalcohols. And here's an example of ribose, and this is the 2R, 3R, 4R version of ribose. And over here, looks like we've drawn the mirror image. And so this is the enantiomer of ribose. It's still called ribose because it's the same molecule, exact same connectivity. It's just the mirror image. So this will be 2S, 3S, 4S. Or in short, we could just call this plus ribose. Because when the optical rotation is measured, we can, sometimes this is called the specific rotation. Once we measure the rotation, once we measure the alpha, the angle, and the polarimeter, we adjust it for the concentration and the path length and that sort of thing. And we we report it in something that looks like this. We call it the specific rotation. This shows that it was the sodium, the D line of a sodium light was used. It was 20 degrees. So this is kind of what it looks like when you report it. And what is found is that ribose minus ribose, the 2R, 3R, 4R, has an optical rotation of minus 19 degrees. So it rotates the plane of polarized light in a counterclockwise direction for 19 degrees. And so the other enantiomer is going to also rotate at 19 degrees, but it's going to go in the other direction. It's going to go in a clockwise direction. Okay, so sometimes we refer to the different enantiomers, the plus enantiomer or the minus enantiomer, and that will be a way to distinguish between the two. Okay, every other physical property that you can imagine, melting point, solubility, spectroscopy, are going to be exactly the same. So for example, the melting point here for both enantiomers is 88 degrees. Let's compare that to, and so here we have two molecules which are enantiomers of one another. Every stereocenter has been inverted, and we now have its mirror image. Now if we compare this structure to the next structure, you see that one of the chiral centers has been inverted, but the others haven't. Okay, so now we're comparing molecules that are diastereomers of each other. They are no longer enantiomers, they're diastereomers. And so this is a different sugar. This is called arabinose. This is the minus arabinose. And what would we predict its rotation to be? That's not something we can predict. We can't predict it. We have to take the measurement. We have to put it in a polarimeter and measure the optical rotation. There's no way to predict it. We can't say that if it's an R, it goes one way, or an S, it goes another way. The only way we can ever predict an optical rotation is if we know the optical rotation of one enantiomer, then we know the optical rotation of the other enantiomer. Otherwise, it's just something we have to measure. And so here it is, very similar molecule, and this rotation for arabinose has a 104-degree rotation, and this enantiomer has it in the levorotatory direction. It's a minus 104. Okay, what is a melting point? Well, again, not something we could predict. We would have to measure that, and you might think, well, gee, they have the exact same functional groups. I would expect them to be pretty similar, but there's actually quite a big difference. Instead of 88 degrees, we have a melting point of about 162. It's almost twice the melting point, and the difference there reflects this the stereochemical shape of this sugar, because remember, the temperature of a melting point has to do with how tightly the crystals pack together. And so, so the arabinose molecules must, because of their 3D shape, must have a better packing in their crystal structure, and that's what accounts for their higher melting point. No way we would be able to predict that, but it's just a nice illustration on how the physical properties between diastereomers are totally different, but between enantiomers, they are the same. Okay, so when do enantiomers behave differently? It is possible for two enantiomers to behave differently, and that's going to be when they interact with other chiral objects and other chiral things. So for example, if we take our favorite pair of enantiomers, our right and left hand, when do they behave differently? Well, if you tried to pick up a water bottle or a coffee mug, let's say, something that is a symmetrical object, you would be able to do it equally effectively with your right hand or your left hand in terms of how it fits with the coffee mug. Okay? And so in this case, we would find that there is no difference on how they fit. Okay, but what if I had my right and my left hand, and I had a right-handed glove that I was trying to interact with? Well, of course, my right hand would fit perfectly into the right-handed glove, but my left hand would not fit at all. So in this case, we observe a difference between the two enantiomers. So why is that? What's the difference? Why is one going to be indistinguishable and the other is going to find a difference? Well, that's because a coffee mug is a symmetrical thing. It is achiral. And because it's symmetrical, my right hand and my left hand are going to see the same thing when they try and interact and dock with that mug, if you will. But a right-handed glove is something that is chiral. And so when you bring in a chiral molecule with another chiral molecule, they are going to interact differently. So that's exactly an example of that. Now, we just saw that the two enantiomers are going to interact differently with polarized light, right? There's a difference there. One is going to be dextrorotatory, and one is going to be levorotatory. So what does that tell us about polarized light? It tells us polarized light must be chiral in order for there to be a difference. And it is. It's because it's a helix. It's actually helical, and you could have a right-handed helix or a left-handed helix. There is chirality to it. So that's why a polarimeter is able to distinguish between enantiomers. Let me show you one other interesting example. Here's another enantiomer pair. This molecule is called carvone. And you could call this S-carvone and R-carvone because there's just a single chiral center there. So that would be some nice practice to confirm that you would come up with S and R. Or you could call this plus carvone and minus carvone because that's their optical rotation. You could see they're equal and opposite. But there's something else that's very interesting about carvone. S-carvone, the dextrorotatory enantiomer, tastes and smells like caraway seeds. Those are the little bitter seeds that you have in rye bread. While R-carvone tastes and smells like spearmint. That's kind of a minty flavor that you might have in chewing gum or something like that. So exact same molecule, exact same three-dimensional shape. We simply have this mirror image relationship, but a huge difference in how we perceive it in our bodies in terms of its taste and its odor. So what does that tell you about the receptors that must be in our noses and in our mouths? They must be chiral. So our odor receptors and our taste receptors must be chiral in that they can distinguish between enantiomers. One enantiomer, if we have an odor receptor here, one enantiomer is going to fit differently than another enantiomer, and that's going to send different signals to our brain, and we're going to interpret that differently as a different odor or a different smell. So the whole world of stereochemistry suddenly takes on a whole new light of importance, because when you think about naturally occurring compounds, things like amino acids or sugars or enzymes, these are all chiral molecules. And they exist in nature typically as just a single enantiomer. So when we look at biochemistry, the field of organic chemistry, the organic chemistry in living systems, we'll find that stereochemistry is hugely important, and those stereo centers give rise to a particular behavior. And in fact, the other thing to keep in mind is that drugs that we take, pharmaceuticals, are often chiral. Almost so many of them are chiral molecules. And so that means, so for some example, ibuprofen, the pain reliever, is a chiral molecule, and it's sold just as, we'll talk about how that's sold in just a minute. Thalidomide is a chiral molecule, and it was discovered years ago that one enantiomer was something that had very good benefits, but the other enantiomer was something that had devastating effects. It was tetratogenic and caused birth defects. And so hugely important to consider the stereochemistries of your molecules when you're dealing with things that are going to be entering the body, especially like pharmaceuticals, because the different enantiomers might behave differently. Let's talk about something called racemic mixtures. That, by definition, is what we call it when we have a one-to-one, exactly one-to-one mixture of enantiomers. If we have equal amounts of two enantiomers combined into a single mixture, this is now something that's going to be optically inactive. In other words, the alpha is going to be 0. And think about it, if you have a certain amount of the levorotatory enantiomer and you have that exact same amount of the dextrorotatory enantiomer, those are going to cancel each other out, and a net result is going to have no rotation whatsoever. So these are optically inactive, and in fact, for the chiral drugs, most of the chiral drugs that are on the market, such as ibuprofen, those are sold as racemic mixtures. So you have both the plus and the minus enantiomer in the tablet that you're taking, and again, that has very important ramifications for the pharmaceutical industry. Perhaps just a single enantiomer, one of the enantiomers, is stronger acting or will last longer. Maybe the other enantiomer is responsible for some side effects or that sort of thing, causing nausea or upsetting your stomach or what have you. So because many of them are sold as racemic mixtures, a lot of research is going into, well, what if we had just a single enantiomer? Would that be more potent? Would it be longer lasting? Do we need a different patent for that? All sorts of interesting ramifications go on for that. Now, as you might imagine, if I had a racemic mixture, let's say of ibuprofen, and I wanted to separate that mixture into the two different enantiomers, that's going to be quite a challenge since enantiomers have identical physical properties. I can't just do a distillation. I can't do a crystallization. I can't separate them the ways that I would normally separate organic compounds because they behave so similarly. So there is a process, though, that exists that can be used, and this is used very often in the pharmaceutical industry, and it's called a resolution, the process for separating enantiomers. And so let me just show you how, in general, that process would work. Let's assume that we have a racemic mixture here. So this is represented by an equal mixture of plus enantiomers and minus enantiomers. What we're going to do is we're going to take that racemate, or racemic mixture, and we're going to treat it with some kind of chiral resolving agent. So this has just a plus rotation or a minus rotation. It's some chiral agent that we can get from nature or that's commercially available. And we're going to react it with the racemate and form some kind of interaction that is temporary, that is reversible. And so we're going to have our plus resolving agent now associated with both our plus and our minus racemate components. And when we compare the resulting structures, we see that these are in fact now diastereomers. When you compare a structure that has a plus-plus to a structure that has a plus-minus, those are no longer enantiomers. They can't be mirror images. One part of the molecule is the same configuration. The other part of it is the opposite. That's our definition of diastereomers. And because they are diastereomers, they have different physical properties. And if they have different physical properties, now we can separate them. So we could do something like recrystallize them or do a chromatography, something like that. Recrystallization is a very common method here. And we can effectively separate the plus-plus diastereomers from the plus-minus diastereomers. And then all we have to do is we can remove and hopefully recover, so we can reuse it, our chiral resolving agent, thus freeing up our enantiomers, and now we have these in two separate containers. So we have a container of just our plus enantiomer and a container of our minus enantiomer, and we've effectively separated the two enantiomers. This process is called a resolution of a racemic mixture. Now, a racemic mixture is what we call it when we have an exactly one-to-one mixture of two enantiomers, but it's also possible to have unequal mixtures of enantiomers. Those mixtures are described by what's known as an enantiomeric excess, or EE for short. This is a measure of optical purity, is another way we could describe it. How pure is it in terms of being just a single enantiomer? And EE is defined as by comparing the measured optical rotation and dividing that by the pure optical rotation. When we take that and convert it to a percentage, that number is what we describe as the EE, the enantiomeric excess. Another way to describe EE is to say that the EE is the difference between the percentage of the major enantiomer and the percentage of the minor enantiomer. So for example, if you had a 100% EE, 100% enantiomeric excess means you have pure enantiomer, 100% in excess of a single enantiomer. Your EE is 100% of one minus 0% of the other. Okay, a 0% EE means you have no excess of either enantiomer, so that means you have exactly one-to-one. You have a racemate, or a racemic mixture. In other words, 50% of one enantiomer and 50% of the other enantiomer gives you an EE of 0. So 100% means I have pure enantiomer, 0% means I have exactly one-to-one mixture, and any EE percentage in between there means I have some kind of mixture of the two enantiomers. Let's take a look at some examples. Here we have an alcohol that is the S alcohol. And it's known that this pure S alcohol has an optical rotation of plus 20 degrees. Okay, so just like other physical properties like melting point or boiling point, this is something that can be measured. It's reported in the literature, and you can look that up. So do we know what the pure R enantiomer would have as an optical rotation, as a specific rotation? If we had a pure R with none of the S in it, we would expect that it would have the same magnitude but the opposite sign, so it would be minus 20 degrees. What if we had the racemic alcohol? In other words, an equal mixture of the S alcohol, where this is a dash, and the R alcohol, where this is a wedge? We could describe that as a plus minus, is a way to abbreviate a racemic mixture. What would the optical rotation be there? If we had exactly equal amounts, we would expect it to be optically inactive. Oops, not degree C, excuse me. It would be a 0 degree rotation. That's what we expect for our racemic mixture. What if we had any other mixture of the R and S enantiomer? Any other combination of those? Where would you expect the alpha, the optical rotations to be? Well, we would expect that they would be somewhere between minus 20 degrees and plus 20 degrees. So the minus 20 and the plus 20 are the extreme rotations you can have if you had pure R or pure S. The presence of any other amount of the other enantiomer is going to lower that optical purity and reduce that rotation and bring it closer to 0. So for example, if you had to sample this alcohol, it was pure alcohol, you took an NMR and you saw no other peaks in here, so it's not contaminated with any other molecule, but its optical rotation is plus 10 degrees, then what is the EE for this sample? Well, remember, EE is defined as the observed optical rotation divided by the pure, or the literature, optical rotation. So we see that our sample has a plus 10 degrees. And the pure, well, because this is a plus, that means I have an excess of which enantiomer? What do I have more of? I must have more of the one with the plus rotation. So I have an excess of S. But there's some R mixed in there, and that's why our optical rotation isn't the maximum that it should be. So I have plus 10 divided by plus 20 means that I have a 50%. We're going to multiplying it by 100% to convert it to a percentage. We have a 50% EE for this sample. A 50% EE. So what does that mean for the percentage breakdown? How much of each molecule do we have? Well, remember that the other way to describe EE is the major percent minus the minor percent. And we could do a simple algebra problem to solve this so that it comes out to x. We could set the major percent as x, and the minor percent would be 100 minus x. Okay, so we could do this and solve for x, and what we would find is that we have 75% of the plus enantiomer and 25% of the minus enantiomer. Okay, now again, 75 minus 25 would come up to 50%. So you can see we have an excess, a 50% excess of the plus enantiomer. And you can imagine that of this 75%, we have 50% that is our excess, and 25% is going to combine with this 25% to be racemic. So it's like half of our mixture is a racemic mixture with plus and minus, 25% of each. The other half of the mixture is pure plus. So that's why our optical rotation is only half of what we're expecting, because of the entire sample. Let's say we have a 100-gram sample, only 50% of it is the pure plus that's going to be giving the optical rotation. The other 50% of it is a racemic mixture that has no optical rotation. So just want to give you a feel for how to work with the EEs. Okay, one more example. What is the percent composition of a sample with 90% EE? Now again, that means we have 90% of one enantiomer plus 10% of the racemic. So we have 5% and 5%. So that means we have 95% of one enantiomer plus 5% of the other enantiomer. This is just one way to think about it. Again, you could solve it algebraically like this to set one to be x and one to be 100 minus x, and then the difference now would be 90%. But the difference between 95% and 5% is 90% EE. So 90% EE equals 95% minus 5%. So if you have a 95-5 mixture of two enantiomers, it would be described as having a 90% EE. And you would expect the optical rotation to be 90% of the maximum, the literature value for that sample.